Okay, so I guess we could start. So first of all, thank you all for joining for this first online meetup. It's great to have you all of you here, and I hope we will have a great discussion and maybe a follow-up meetings in the future. So I hope it is fine for this meeting to be recorded for all of you. Please say something if you don't want to or something like that. And another thing I want to say, is that so we don't have a premium account for Continual AI on Slack. So sorry, on Zoom. So what is going to happen is that after 14 minutes, roughly from now, we are going to be kicked off this meeting. And so what I ask.
What's up?
Hi everyone. So what I ask you to do is to just click again on the link to join this meeting so that we can continue our conversation. I mean, I wanted it to be like also a very, let's say, short meeting, not 2 hours long, just I don't know, an hour meeting or something like that. So I'm sorry that we could not fit everything into the 40-minute spot, but I mean it's still too short, so we have to rejoin, and then maybe after 20 minutes or so we can all leave the meeting. So again, thank you for joining, and so we have here. I've seen Timothy Lesor, Gabriele Graffiedi here. Martin, are you there? Are you there? Great.
Yeah, I am. I just muted.
Yeah, that's great. So we have Martin, and then Massimo Caccia. Are you there?
Yep.
There. So that's great. I can see you. Great. So I invited them to speak a bit about generative models for continual learning, because I know they have published something on this topic, and they have a great experience on it as well. So I was hoping, to hear from them something about, their work, their research, or their ideas about the topic. And so we can start maybe with a 5 minutes introduction from them. It's up to them what to say about this, and then we can start with a few questions from the community to see, if we can start an interesting debate on the topic. And I mean, it would be great if you guys could answer to these questions. But I mean, anyone here, I think, can say whatever he thinks about the topic, and so that maybe we end up at the end of this meeting with an enriched view about this topic and a few ideas we can put into practice in our research. Okay, so who wants to start? Maybe Gabriele?
Yeah. Okay. Okay.
Oh, what happened? No, we just
Okay. Just some minor problems. Okay, I'm Gabriele. I'm a PhD student at the University of Bologna with Vincenzo Monaco here, and I've been working with generative models for 2 years, almost 2 years. I started with generative adversarial networks, mainly for image-to-image translation, file transfer, so create some nice images, with some artistic style, etc. My master thesis showed one of the first use of these generative adversarial networks in the field of image defogging. So we try to remove fog from images, especially images with heavy fog with a very low visibility. The last month, I started to work on continual learning, and I tried to join continual learning with generative models, especially in 2 different directions. The first one is use generative models to produce some replay patterns, for example, to generate some images or some sequences for replaying them to the continual learning model. This is the first way, in my opinion, to use generative models in continual learning. And another way can be the generative model is itself a continual learning model, so trying to include some continual learning technique in the generative model with the goal of trying to use the generative model to learn some distribution of data continually. So, for example, first try to learn a distribution of cat images, after that dog images, but not forgetting how to generate cat images. And finally, we are working now on a project about generative replay, so replaying patterns to continual learning with generative models. We are trying now to not produce only images, so not replaying at the pixel level or the image level, but also on the latent level, so trying to produce some latent activation of the neural network. We are encountering some problem because mainly the main problem is that the model thinks for images that the generative models, for example, the GAN or the variation autoencoders that work well with pixel and images, in fact, don't work very well on this latent feature. So this is my main question, if you have some experience in this kind of generative production of latent features and activation. I think 5 minutes is all. So maybe next. Who want to be the next one?
I don't mind.
Okay, great.
Cool. I haven't prepared anything, but I'll try to do a quick intro. I'm not currently working on generative models anymore, but I still think they're super interesting for continual learning. I guess some motivations for me would be if you use a generative model component in your, for example, classification task, maybe your generative model is going to model some features that will later be useful, which you don't get in if you like train a classifier continually. Like if you differentiate cats and dogs, you're only going to learn the discriminative features between them on the first task, and then when you get to the second task, you're a little bit fucked, sorry, because you haven't modeled enough features. But with generative model, you have the promise that you can model more features that will later be useful. So it seems like a natural way to do continual learning. And I guess also for me, what's exciting with generative models is maybe you can use them to know what you don't know. So I think that's like when they will deploy these continual learning agents in environments, and it will be important for them to know what they don't know, so they can leave the inference mode and start the retraining again. And maybe you don't want them to always be retraining, because retraining leads to more forgetting. So they would need to be smart about what data they use to retrain. So knowing what you don't know, I think it's going to be important. And I think you might be able to get that with a generative model, and maybe not with such sort of like the uncertainty you get from the softmax, which I don't really believe in. And I guess personally, I worked on generative models to use it as a memory. Like I guess 99% of the continual learning papers using generative models. So use them for generative replays. I was using VAEs. And I guess I have one paper, which we just presented at NeurIPS. And in the paper, I think we did something pretty cool with the generative model. So instead of just randomly generating data with the generative model to repractice on, we're looking inside of the latent space of the generator to find exactly what the model is forgetting, and then we're training on that data point. So basically, because we're exactly training on what we're forgetting, we're experiencing less forgetting. So we're using this generative model smartly. So yeah, I think that another point for generative model is that like they're a memory, and it's easy to look for something in the latent space because it's a much more compact space than just a buffer of example. Oh, hey Natalia. Hello.
Hi Natalia. Well, you can continue, Massimo. Sorry about that.
Well, that was the end, basically. So
Okay.
I think that it was the end. We're searching the latent space for what we're forgetting. I guess to be more technical, we're doing so. We have a classifier, and we're going to do one virtual update step on the incoming data. So this will now we'll have two models, one that's better at the current task, but probably forgot something. And now we're going to maximize we're going to search inside the latent space of the generator to find a sample where the loss increased the most between the two models. So we're doing gradient descent on the latent codes of the generator to find a sample that we're forgetting. So maybe we're learning the digit number 8 and we're forgetting the digit number 3 because they look alike. So this little search in the latent space will find that we're forgetting the digit 3, and then we're going to repractice our 3. So that's sort of the gist of it. But yeah, that was my last work on generative modeling in continual learning. So I guess that's it for me now.
Cool, thanks, Massimo. And so, Martin, do you want to
yeah,
say?
Maybe. I think maybe I could go next because it's quite related to what he's just been talking about.
Okay, great.
Because it's essentially very similar. So I'm a PhD student in my last year, and we've done some work on generative modeling for continual learning, but also like some neural architecture search. And from the generative model perspective, we have 2 works, and both of them actually are more focused on less of just the catastrophic forgetting component of continual learning, but more so on the open world learning, meaning what he's just been talking about, naturally identifying what you've trained, what you haven't seen yet. And because that kind of implies for continual learning that you don't have a task oracle during inference, and maybe you don't have necessarily even task boundaries during training. And so what we do is, we have one work that's we presented at ICCV that examined the latent space property for basically the latent space structure for out of distribution detection, depending on the model choice and variational autoencoders. So basically we examine how uncertainties help us in out of distribution detection on softmax output if we make it discriminative, versus if we learn the data distribution, versus if we learn both, compared to things like Monte Carlo dropout. And some things we figure out that you're basically almost always better if you look at the latent space structure and like do a distribution fit instead of looking at some proxy things like reconstruction loss or softmax or activations or whatever.
Can I ask a question, Martin?
Sure, of course.
So what metrics specifically were you using to detect out of distribution samples with the VAE or with the generative model?
So basically there's 3 choices of models. You can have a variational encoder plus a classifier. You can have a variational autoencoder, so just encoder decoder. And you can have one that's basically both. So basically you classify in latent space and have a decoder. So the metrics you could take a look at is reconstruction loss, classification loss. You could take a look at classification entropy, so the entropy over the output predictions of the softmax. Because it's because it's variational, you could either now sample from the posterior, like multiple samples, so generate like 100 Zs and get the uncertainty, or you could put like the uncertainty over the weights by basically having the distribution on the weights and doing Monte Carlo dropout. So have a dropout on every layer, sample the entire model, and then take a look at any of these metrics actually. Plus the last thing we take a look at is it's like an extreme value theory fit on the latent space. So basically what you do is you fit the distribution with some other distribution and basically cut that at some point. So meaning let's say your latent space has a blob, then you fit that blob, and anything that lies outside that blob is considered outlying.
Yeah, okay. So the KL of the latent codes.
So some distance metric, something, whatever.
Yeah, okay, yeah, cool. That's cool. That's what's the name of this paper?
Maybe I'll just link it actually.
Yeah, please. It sounds super interesting.
Can I link it actually? Yeah, there's a chat. Right?
Maybe the Slack channel or.
Yeah, there should be a chat you can use.
There's a okay.
Yeah,
so there's
great.
a chat thing here.
Well, maybe to keep up, it's better to put it in the Slack. So
okay, I'll put it in the. I'll put it in the Slack after. Anyway, so we kind of got motivated by that to actually go like the continual learning route and do something maybe quite similar to what you just said, but instead of taking a look at what changes the most, basically instead of sampling generically from a latent space, we would like to sample the space that has high density, meaning we like to sample where a model is most confident and has seen the most data, and exclude anything that might be, for example, if you take images of these MNIST digits, generative models typically interpolate between numbers when you go towards specific regions. So you want to avoid that. So you basically only sample the very most specific areas where you know there's high density in your latent distribution. I'll also link that paper. Unfortunately, we weren't as lucky as you were in terms of getting it accepted. But
which conference?
iClear. It's just happened.
Oh, okay.
Just got. You can read it on Open Review. It's a little bit unfortunate. Because basically we didn't get a reviewer. That's the first thing. But anyway.
What? Zero reviewer?
No. We got reviews, but like late and so on. So there was some.
iClear this year was really weird. But,
anyway, anyway, you can read the paper. I think it's fine. So what we basically combine there is we combine the question of can we have a model that's like a single model that's both generative and discriminative? Can do continual learning by generative replay, improve the regular generative replay by sampling in distribution samples, versus reject all outlying distribution samples so that we can basically learn in an open world scenario.
Yeah.
And we do that for some like image and audio data set. So.
Oh, shit.
Cool.
Okay.
I think that's that's about it from my side for now.
Cool. Thank you very much, Martin. Anyone
okay,
has?
I think
okay, Tim, do you want to speak? Yeah.
Okay, I think it's my turn. So thanks everyone for being here. Thanks for the introduction. So my name is Timothée Lossor. I'm a PhD student in Paris. I work between Paris Engineering School and the company Thales. I'm also in my last year of PhD. So right now I don't do any experiment anymore. I'm just writing. I study in my PhD continual learning, and in particular the replay methods for continual learning. And I started 2 years ago to work on generative replay. So we had a couple of paper on generative replay for classification, and we study how generative replay can learn continually. So we try different settings to continual learning the generative model and see what is the best performing solution. And after we tried in the classification settings how we can apply a generative replay for continual classification. So basically what we've seen is that it works pretty well as long as the generative model is good. I mean, of MNIST or fashion MNIST, it works quite well. But if you go to other settings, like Cypher 10 or Core 50, it's much more difficult to train your generative models and therefore to learn continually. Anyway, I think that there is big progress in generative models, so maybe in few months or a few years we could learn in difficult setting with generative replay. I started to work on generative replay because there is several assets that make it very interesting for me. So for me, for example, there is a better understanding of the data. The fact of if you do learn classification, the fact of learning also to generate the data can give you a better understanding of it, or maybe a better generalization, because you can maybe generate data that are not in your data set with your generative model. The generative replay is also model agnostic. Whatever the classification model you use, the generative model don't care and just generate what it can. It's also agnostic to the number of tasks and the number of class, which is pretty nice for the open world learning you were talking about, Martin. And what I find interesting also is that you have control of the memory. If you don't want to remember something, you can just stop replaying it or just don't use the sample you are generating. I find it very interesting to be able to control some of your memory, and that's something you cannot do in other approaches like regularization, for example. And another thing is that with generative replay, you can have a new interpretation of your data with your classification model. I mean, when the data see the model sees the data for the first time, it has some kind of understanding of it because it has some representation of data. But maybe later it will have some more representations or more feature extractor. And the fact that you are able to generate again this data, it makes you able to better understand it based on your new knowledge. Okay, and the shortcomings of generative replay for me was it's difficult to assess your generative model when you learn continually. I mean, it's difficult to say, okay, I think my generative model is good, but that's the problem of everybody that try to train generative model. Generative models are also very long to train, and they are very unstable. If all your memory are in your generative model and you somehow diverge, you broke all your memories, and that's very bad. So that's it. So to resume, I mostly worked on simple classification setting, but I found very interesting what you were talking about smart sampling of your generative model for continual learning. It's true. I think we could have a big increase in performance with this smart sampling thing. And sampling in latent space, I think it's very interesting, but maybe it's dependent of the feature extractor. If you learn to generate your latent features, but your feature extractors change, maybe you are able to generate features that are not up to date anymore. So it might be difficult. I don't know. So thank you.
Cool.
Okay, cool. So thank you very much, team. So maybe we can start having some questions from the other participants if they have some.
I have one if nobody in the crowd comes.
Of course, you can start that.
Yeah. Okay, cool. So I guess one question I've been thinking is if you're using generative modeling only for generative replay, then you don't really need to train the generator on its own samples, right? You could just freeze the model, add some capacity, and then only train the new part to generate the new data, and then use the task label to generate what you need, because you don't care that your generator needs the label to generate if your classifier can classify without the test label, right? So why do we try to train our generators continually without the need of the task label at test time? Just seems easier to train them and freeze them and grow and so on and so on. And then you never train on your own samples. That makes sense? Or I can rephrase if it didn't.
I think the thing that your classifier can give the label, for me it was also interesting that you can confront what the generator think is generating and what the classifier think about it. So you can confront these two knowledge and see if they are agree. I don't. Do you refer to something in particular? I don't remember seeing a paper that froze the part of the generative model or make it grow in some ways.
There is this CVPR paper. Actually, it's Alexei, which I was talking to you about last time.
Okay.
I will find the link and post it. But basically, I found what he did was super smart. He was just his classifier is trained continually without the need of the task label at this time. But his GAN is just trained. It's never trained on its own sample. He just freezes the model, keeps a memory of the mask, and then grows it to generate the next digits and so on and so on. And then his generation is like really good because he leverages the task label, and he basically gets no forgetting in his generative model. So it just seems like a easier way. If you're only interested in generative replay, then I wouldn't see why you would train your generator on its own samples if you can do that.
So, I mean, this has two implications, right? The first one is that your generator is a separate model than your discriminator. So
yeah, right.
If you actually just have one model, then you need to train it on its own samples.
Yeah,
that's the first one. So that already gives you like a memory overhead of factor 2. The second thing is, if you move across tasks that are not like class incremental in form, like something really extreme, Go, MNIST, ImageNet Audio or something, you would obviously like to reuse as many features as possible, but get rid of all the overparameterized features. So let's consider you take a ResNet and you train that on MNIST, and you're just going to freeze the capacity and add more to it. You've basically just heavily overparameterized your MNIST setting. Whereas if you train it continually, it's going to press the features together to make room for, like, you don't necessarily need to grow the model, because you can actually just readjust whatever the capacity is, right? So
yeah. No, I mean,
that works. That works if at any point in time you also have an algorithm that gives you whatever effective capacity you need for that specific task. Otherwise, you'll just have massive memory overhead. That's my view.
Yeah. I just I don't see memory as a big bottleneck. I see compute as a big bottleneck.
Well, it's the same, right?
And I guess in this case, it would be the same.
It's related.
Yeah. Okay, yeah. But still, like, training again continually on its own samples, like, I think we can all agree that at some point, like, it's going to break, right? So unless you have some smart tricks to keep some previous models and then you go back if they broke or something. But I mean, just seems like if I was to deploy a continual learning algorithm in real life, I'm not sure I would use again in 2020, but maybe in 2030, I don't know. But today it seems like
so guys, we have like a gift from Zoom, so we have removed the 30-minute time limit for this meetup, so we can continue. And okay, that was just awesome, great news. Cool. Yeah, continue, please.
I think that was it. Yeah.
Okay, so no, it's quite interesting what you were saying also, Massimo, on the fact that you could freeze somehow the generative models right after each task or batch, or that it is in that case, it's just a memory overhead, and they're not going in terms of computation in that case, because you can just go inference on them and regenerate the data that you encountered before. So they are often related, computation and memory overhead, but in some cases you could do that. But I'm not only interested, at least this is my perspective, only on the practical implications and applications of continual learning, but also on an idea of a sustainable continual learning algorithm that works like a bit more like our brain, or in a sustainable and efficient way, and also in terms of memory. And so that's why I often try to avoid approaches in which you grow continually, also in terms of memory, overhead. Because in that case, you would add like a linear, at least, memory overhead after each task that you encounter. So, well, yeah, that was my little perspective on that. That we every time in my dissertation, and I mean, every time I try to define continual learning, I try to say that one of the most interesting thing of continual learning is that I like to define it with a upper bound in terms of computation and memory. So they should say, I mean, they should not maybe stay constant over time. They can grow and decrease, but they should have an upper bound. So this idea, if the data continues to arrive and we have to learn from them, you can change your resources that you give to the system to learn new things and to generalize over time. But in the end, you should be bounded in terms of memory and compute. And that's the real, I mean, a game for me. That's the real continual learning algorithm that can somehow manage to learn and generalize and adapt, but also being constrained in terms of hardware, let's say, resources that we give to the system. So that's just my perspective and the vision, let's say, towards solutions that can be already aligned with this vision, right? So that's why I try to. But of course, for practical applications, the idea of having a few snapshots of models here and there, and a few examples from the past that you keep in memory, these are good approaches, of course.
Makes sense. So I guess I have one question for you then, because for me the compute makes sense. Like, we should try to make models that don't increase in computing needs, but I cannot convince myself that we need the same for memory, because for me memory is extremely cheap. You can always put something in the cloud, you can buy a S3 bucket and put it there, and it's really, really cheap. It's just, you're going to spend compute getting that stuff, but I don't see why we're putting constraint on our memory. Like, for example, here's my result when I do replay with Cephar and I only keep 10 samples. Well, it doesn't make sense because the samples are living somewhere in the cloud. So why would I evaluate my model on these really, really tiny memories? I think we should just, for me, it makes more sense to study continual learning in like 2 dimensions instead of 1. So right now, I guess we're just doing accuracy at the end, and it would go. But maybe we should study accuracy in like compute space, and then it would make, we'll see that, oh, okay, we can get better results when we do a shitload of replay, blah, blah, blah. But I don't see memory as like an important third dimension. I think it can always be put back to compute. That's what I'm saying.
With this argument, you kind of go down the rabbit hole, don't you? So because this extends to like all of deep learning. If you start with this argument, you might as well say, you just pick core sets, for example. Core sets are going to identify the most relevant examples of your data set. You can scale this to the majority of the data set. So you store like half the data set because that's essentially memory. Why does it need to be generative? And in the end, no one's actually taking a look at like the small sample behavior of deep networks. Like, how many samples do you actually need to train a deep network? How many samples do you need to train generative replay, and so on? So this kind of loops all the way. Because if you say memory isn't a constraint, you just store everything.
But why not store everything? That's what I'm saying. Maybe I didn't understand your argument perfectly, actually.
I'm saying, like, if you say that, you're basically saying just store everything, and then you just store basically all the real data. I guess the entire assumption is that you don't want your memory and your compute time to just scale linearly with the data.
Of course, I'm with you with compute, but I'm not with you with memory. For me, it's weird to constrain our memories. It's just, it's compute, it's accessing that memory that's costly. But
okay, so let me ask you a different question.
Yeah.
If you say memory is not limited and you basically just store the entire data set, how will you limit compute?
I wouldn't limit compute. I would just show that my model is better in accuracy compute space.
I kind of agree with Massimo on this question of we can resume everything on compute, because you cannot say in a real life scenario, I mean, you cannot say I will save everything, because saving everything will be you will need too much computation to access everything. So you are not maybe constrained by the memory, but by the computation that you need for this memory.
I just want to add something to that. This is Eric Laukin, by the way. If you have, I'm the anti-experience replay guy, so I have somewhat strong opinions on this.
Sure.
So if you do experience replay and just have this massive replay buffer, and then you say, oh, only the compute matters, you can only sample so often on some percentage of that replay buffer. So if you really want a good sampling of all your memory, that grows linearly with the replay buffer. So if you increase the amount of memory, you're also increasing the amount of compute.
Yeah, I don't think so. You can have a bigger memory and do the same amount of replay.
Yeah, but then you don't learn as fast.
What do you mean?
You're literally sampling on a smaller portion of what you remember.
But that's good. I'm not.
No,
so
because then you forget things. Say if your replay buffer is infinitely big, like it just stores, not infinitely, but let's say the lifetime of a whole human, and you're sampling like one per time step randomly, you're probably just going to forget 99.99999% of it because you never sample it.
Yeah, but wait.
So you need a linear scaling amount of sampling.
I think there's something weird here. So if I'm keeping, so let's say we're doing MNIST, I'm keeping all the samples and you're keeping one sample per class. And we do the same amount of replay. So I'm equally sampling ones and twos and you're doing the same. The only difference between me and you is like your thing is super noisy because you're always sampling the same digits.
Well, sorry, I don't know. I don't actually do replay at all because we parse models that integrate data continuously into like a buckets almost. So we never have to replay because it's always in the model.
But weren't you defending experience replay with a smaller buffer?
No, I was saying no replay.
Okay, sure, no replay. Because, okay, first, of course, but so compute is the bottleneck. Replay sucks because of compute, but memory, we don't care about it, right?
Yeah, but the experience replay buffer also increases compute is my argument because you have to sample more often to distribute your sample. You will forget within the replay buffer.
I guess, okay, so what I'm saying is just, we're comparing two experience replay methods. One as a big buffer and one as a small buffer. They have the same amount of compute, both of these algorithms. Which one would win?
The one that's better constructed to capture the data distribution.
Exactly.
No,
I mean, the problem
everything is fixed. Sorry, everything is fixed except the buffer size. That's it.
Yeah, but see, the difference is in how the buffer is constructed. One constructs a buffer of maybe 100 samples because that captures the distribution the best. Like if the distribution has 10 modes, it basically captures your 10 modes in some way. The other one just uniformly samples, but your data actually isn't uniformly distributed. Not every sample in your data set is equally important for training.
That's probably a better way of explaining what I meant.
I think that's what you meant, right? Like,
but I don't think that's.
I mean, we always assume this. It is. We always assume like data is IID uniformly distributed, but it actually isn't.
But I don't think it's on the point that I'm saying. I'm just saying, okay, you can be smart about what you put in your buffer and what you retrain on. I'm just saying making it bigger can only be good for you. If you need to use that memory, don't hold back. That's just what I'm saying. Because
okay, I agree, but it's the same question. Basically, the one question is figure out a scheme to sample from your data distribution to capture it efficiently so that you construct a small buffer. And your question is don't care about the buffer, just have the big one, but still figure out the sampling scheme because you need to sample from it still. If you sample uniform, it's the same question. It's the same question, just from two different angles.
So do we agree that memory shouldn't be a constraint? Much?
I mean, memory. No. We agree. What should be constrained is the amount of samples that you use when you update. Yes.
Sorry, the amount of the compute.
Yeah. So the amount of samples you take for updating. Yes, that is basically the compute.
Yeah, I mean, I agree on this point, especially with respect to the experiments and current applications that we have nowadays. But I mean, if I try to look more into the future, and you think that we're going to integrate more and more data, high-dimensional data from very different sources, multimodal, maybe streaming data. I mean, and if you look at the curves of data generation over time, I mean, how they're growing into the world, and our ability to keep up in terms of data storage, that's not really obvious that we're going to be able to store all the data at all. This is one thing. And then on the other hand, I mean, there will be always, smartphone devices and I mean, your fridge maybe may run a continual learning algorithm. In that case, if you work on dimensionality that are like ImageNet style more, I mean, even a few hundred gigabytes, maybe it's not that obvious that, you want to store that in with your algorithm. So, I mean, my idea is that maybe nowadays you can find very little applications and, they use for this need to be constrained in terms of memory, but in the future you may want to look also to continual learning solutions that are bounded also in terms of memory. That's my guess.
Yeah, especially.
Were you going?
Yeah, just especially for low computational devices or Internet of Things devices, some kind of object that have low memory, have a low computational power. So, for example,
I understand that, but everything is in the cloud, right? You can, if you have compute, you can always access the cloud. ImageNet is in the cloud maybe 500 million times.
It's I mean, nowadays it is like this, but we have also problems using this cloud paradigm for many applications. But I mean, let's think about an application without internet access, for example, or so an application which you don't want to send your data, your private data, to your cloud service provider, and all these things are interesting points to me.
But is that a big part of what the continual learning applications will look like?
Actually, hold on. I just want to add in, I think that it is, at least that's my perspective, because I mean, that's our whole thing, is that we do like continual learning on small devices like Raspberry Pi. Like we can do Atari games on a Raspberry Pi, like just train it on there. But then the more important thing, like where it actually starts becoming useful, is like robotics, basically, which is more far off future thing. Like if we have toy things today, but in the future, you'll probably want continual learning on the robot itself.
100%. But why wouldn't that thing have access to internet?
Well, first of all, it's going to lag it a bit. But why would you do that? You don't need to. It's just like a limit for no reason.
Well,
the reason that make a better algorithm that doesn't need it.
Yeah.
So look, what I don't understand is from the perspective of understanding like your continual learning mechanism, it's for me, it's really the same question. Like what you're arguing about is just the engineering twist on how you want to sell it as an application. I mean, for both things, you need to basically first understand which data examples are the important ones, because either you need to sample them from the cloud, you need to retrieve them, or you need to store them in your buffer. But the mechanism of how you get there is the same thing, right?
The way we do it, it's maybe a bit confusing because we don't actually really use deep learning. We use more like a biological approach. We have a sparse coding system where it only uses a small portion of the neurons, or columns rather, at a time. So when you activate a sample, it only activates a small portion, stores into those, and then doesn't forget anything else. So we just have no need in the first place for any replay buffer or anything. You just sample streaming in one at a time. So in our case, it maybe doesn't make sense for like a replay-based system. But if you don't have replay, there's no point to storing stuff in the cloud. And there's the upside, of course, is that you don't need an internet connection, which is nice in its own.
So basically what you're saying is you have a completely disentangled representation that doesn't suffer from the dense like weights that the neural network has, right?
Yep.
Yeah, so I guess that solves it from a different angle. Yeah.
Sorry, Eric, is this paper online?
We have an old paper, but right now we're mostly just do blog posts, and we have this large white paper. Okay. I can link it in the Slack later.
Yeah,
I may have done it in the past, but I don't remember.
Okay. Thanks.
It's a pretty weird technique. A paper was probably not enough because it's kind of building from nothing. Because it's not really deep learning, so it's closer if you think about it to HTM, which I know is like in the deep learning community, but it only uses the SDR idea. Everything else is pretty much different.
Okay, nice.
So yeah, do you have other questions?
Maybe maybe more technical question about the latent space dimension of, for example, variational encoder. Because I have encountered some problems in my last experiments about how to dimension the latent space, and especially how to be aware of a wrong dimension of this latent space. So, for example, if the regularization loss, the KL divergence is, for example, is not converging, is a symptom of a small latent space or a too large latent space. And if there is some guidelines, or there is some papers, some literature in the field to how to find the right dimension of the latent space of, for example, variational encoder, etc., and which is not try and see what you get and retry and see what you get again, etc., etc., because it's a quite long procedure. And so if you have some advice or anything about that.
So you're talking about the how to design the architecture of a generative model. Like some advice from you experts.
But sorry, why does the latent space size matter for a VAE? Because I guess the KL term is going to keep your codes from going everywhere. The model is going to use the number of dimensions it needs. The rest is going to collapse. I guess if you're interested in compute and memory saving, you could just delete those dimensions at some point. But yeah, it doesn't seem like you need to search the size of that space so much for me.
So I would say you do actually. I think so. I don't know if you're aware of. I don't know if you're aware of the entire like beta VAE plus like the additional 7 papers on top or whatever. I think they start with like beta VAE, understanding disentanglement in beta VAE, disentangling disentanglement or something. So they're all like, I can link them later. So they're all basically papers that investigate this, because what the beta is basically doing is it's putting a factor on the latent space capacity, because you always have this trade-off of if your latent space grows too big, then it's extremely easy to reconstruct, because there's a lot of information from each and every single data instance. Whereas vice versa, it's much easier to fit into a Gaussian if you're low dimensional, right? So,
but if it's too big, the reconstruction won't get better at some point, because you're still paying this KL price, right? That's in your likelihood function. The further you get away from the prior, you pay a price. So you could put that bottleneck to infinity, and you might get the same reconstruction as a bottleneck size of 100.
Yeah, but I think so. In my personal experience, I think that's more because there's a lot of like intrinsic regularization happening in stochastic gradient descents and like latent space units or units leading up to dying. So you'll have a lot that just projects to zero. So it's like, I mean, there's a difference always between like representational capacity and like the effective one you actually have in the end, right? So just because you over parameters doesn't mean your model is actually that big. You could just prune like 50% of the units away without anything changing. So
I guess
within some certain limits, I think this argument holds with the, like, I mean, like I said, it's a regularizer, right? So it's a trade-off. And so the regularizer like KL is very easy to fit if you're low dimensional. and the reconstruction loss is very hard to fit if you're low dimensional.
Yeah.
And then when you move away, it's different.
Okay.
Okay.
At least that's my take on it.
Okay.
But would you see the important term to play with the beta VAE is the beta and not the size of the latent dimensions?
So I don't think you can decouple it, and that's what most people maybe don't really investigate. I mean, they actually, like, whatever the beta experiments do is they always just fix the capacity or fix the latent dimension, and then investigate. But of course, there's a relationship. Like the beta doesn't have the same. This is actually, if you want to know about this is one of the problems we've had with our paper, because people have made a claim of like, oh, but beta does this. But the problem is beta does this only applies to like a specific architecture with a specific capacity and so on. And like when you change it, it does different things because, well, it's basically just a term controlling information. So.
Okay, you know more than me on this then.
I think it's a really difficult thing. And I think there's a reason why there's like 7 or so papers on it, because it's an incredibly open topic that most people don't want to tackle. But it's very hard because, like you said, like there's very little tools for going beyond like just empirically trying. And I know there's a paper from last year's ICML. It was one of the spotlights that investigated the lower bounds of VAEs. So basically how tightly a lower bound is fit depending on a certain criteria. So basically the data distribution, right? But I think maybe a much better model to take a look at there is a flow model, because a flow model actually maybe has a proper interpretation for data distribution.
Can you link those papers on the Slack channel or in the chat here?
Yeah, I'll try to link them all in the Slack channel.
Okay,
Thanks. So anyone else?
Had a question.
Yeah, if you have one.
Yeah. Hello. I'm Roger. Hello. I'm Roger.
Hello.
Yeah, Martin. So I read the beta VAE before, and I think the beta VAE is more related to the disentangling the latent factors. So I don't know how to relate it to the size of latent space. So the beta factor is the size of the beta is controlling the latent factor to be disentangled themselves. But how it relates to the capacity of the latent space? Sorry.
So I think that's what the initial authors have claimed, but I think there's a lot of evidence by now that this is like maybe a little bit slightly overgeneralized with the disentanglement thing, because they've just tried it on MNIST, and MNIST is very easy to disentangle in the first place. So I mean, I've just linked this in the chat right now, but I'll link it in the Slack later. This is one of the papers, and if you look at something like Figure 1, it's basically telling you like what this means. It means like how much overlap you have between like your Q and your P, and how much of the latent space you actually occupy. So this is actually like capacity arguments. And of course, somehow, because if you only occupy small capacity in latent space, that can lead to disentanglement, because you'll need to find like an efficient way of using very small capacity. And usually that is by separating generative factors. So it's more, I would say it's more of a coincidence than actually like a really solid, sound mechanism to achieve disentanglement.
Yeah, and actually I haven't found many papers that's investigating the size of latent space of VAE or GAN models. It's not too much. So I read some to analyzing the reduced rank, I mean the low rank of latent space of VAE, but not much about using the beta VAE or joint VAE to do this kind of research. Yeah.
So take a look at the paper I just linked. It's pretty good. Like it's also an ICML paper.
Yeah. Thank you.
I think it's very decent.
Thank you.
So you had a question, Martin?
I had a question for Eric actually, because I think something that Eric said, or the general thing that Eric said, is quite interesting in the sense that, like right now, our community kind of, when we talk about continual learning or continual AI, the definition of it somewhat collapses to a lot of catastrophic forgetting in neural networks, and maybe slowly like diverging a little bit out of it with questions like open world learning and so on. But I do think like the majority of the methods like regularization of representations or even the generative replay, they're like extremely focused on specific deep neural network related things, right? So I am actually kind of wondering what you think about it in general. I mean, of course, I know this is supposed to be a generative modeling session, but like, are we actually, if we do like this very limited, like, let's talk about the beta and the generative model thing, which is a very specific kind of generative model question, are we limiting our scope from continual learning because that's more like a systems question, right?
Yeah, well, actually, SDRs are generative, which is so somewhat relates at least. But
Okay.
in general, my philosophy is that you really need to move away from dense representations to do incremental continuous learning. Like you can do continual learning with like known Oracle tasks, and you can even do some with like incremental learning like that. But to really have it be fast, a low number of resources, you need to have sparse representations, which isn't really compatible with deep learning that easily.
Why is that?
Well, sparsity basically decorrelates all your features. So if you're updating, if you get a new sample and you update, you're only updating a small portion of your network at a time. Because, and I'm talking not just sparsity levels of like 50% like ReLUs. I'm talking like 2%, which is actually what the brain has supposedly, 2% sparsity. So what we do in our system is we have used a specific format of SDR called CSDR, which is just more convenient for our particular architecture, where it's basically several one-hot columns, and each column takes some small portion of the input space, and you train it with a reconstruction method. And with this, you form a generative model of your input, and you can insert new samples whenever. It doesn't really matter. And it doesn't forget them. And I've recently shown, I don't know if you saw the posts on the Slack, we did a care RNN thing, and it can remember from one pass through some text all the way from the beginning. Well, because basically those weights are never touched again, because it saw that sequence, and then it's like, oh, never touching it, because the weights are never even updated anymore, because it never activates that pathway anymore.
Nice. That's the white paper you posted?
Yeah, it describes that.
Cool.
It's a draft though, so it's somewhat incomplete, but it still gives a good idea of it.
Nice. Cool. Guys, I need to leave. I have a 11 o'clock meeting. Vincenzo, thanks a lot for organizing this. We should do more of those.
For your talk and your expertise on this.
Thanks, man. See ya.
See you.
Bye. Bye.
There's a room for another question or something like that. I mean, we have been here for an hour.
Yeah, maybe another question. Only one.
Do you want to? So one question I had is some of you guys working on trying to generate back the activations at some latent space for rehearsal purposes? And what are your experiences about this? Is it like tough as generating natural images back, to the input space, or it's somehow easier, or it's more difficult? You use the same losses. I mean, how would you take this problem? I mean, because it would be very interesting to work on replay buffers or whatever it is on in the latent space, because I think that many features, especially in very low levels of every network, they can be somehow shared and are very difficult to change over time, especially if you work in a very specific domain like natural images. So what do you think about this?
So I haven't worked on it, but I saw at ICCV there was lifelong GAN, which literally reconstructed these Zs as input of a GAN. So because if you get the same Z, you get the same output, right? The rest is deterministic. So, and they claimed it was easier. And I know as a fact that most people who do few-shot learning do these kind of things because it's much, much easier to work on like a structured vector than a two-dimensionally structured or three-dimensionally structured image pixel space. That's kind of really difficult.
Yeah, I mean, but also the activations volumes are also 3D somehow structured, right? Volume, the activation volume.
Yeah, so that depends. If you work on, for example, a Z of a GAN or a VAE, then it's not really, right? So that's more like literally a vector.
Right.
So.
And maybe it depends on if you consider that your feature extractor is frozen or not. I mean, if you want to do latent replay, you need a frozen latent space, because if your latent space change, as I said earlier, your replay is not updated anymore. It doesn't mean anything for your neural networks anymore.
Yeah, there's an aging problem, but so let's say that that is completely frozen. In that case, I mean, how would you operate? I mean, what would you do? You would just try the same architecture, the same generative models that you used on the to work on the natural images, the same in the latent space.
I think this is a bit problematic because there is maybe a big bias in the architecture to produce image in the pixel space. But maybe what I would try to do is to use an architecture like progressive neural networks that try to generate a different resolution images, and maybe trying to see if going in a low resolution images might help.
But you don't see these as
this progressive.
Yeah.
Sorry.
No. You were saying.
You know this progressive neural network for generative generative model?
No, what did you say? So you asked for. Can you say the question again?
I didn't ask a question. I think
okay.
I was just saying that you were asking what would you do if you had to generate in latent space.
Yeah.
And I was saying I will use this progressive neural networks that learn to generate a different level of resolution.
Okay, but it is called
a different level of resolution.
It is called progressive. The progressive neural networks proposed for continual learning. Are we talking about that algorithm?
Yeah.
No.
Yeah, I think so.
Okay, the one from Ruzu et al.
No. Sorry. Yeah, no. I'm speaking about. I need to find the paper again. I will send it on
Thanks.
I think he's speaking about things like VQ, VAE, or other forms of models that are hierarchical in nature.
Okay.
Maybe. Maybe, I don't know, speculate.
Maybe Massimo had a take on this, but because he has worked, I think, on trying to generate, interesting patterns in the latent space. But in that case, in his paper, he had like a compression algorithm of some sort, and so it was step of autoencoders, but on the quantized activation. So it's a bit different, but. So I was interested in trying to disentangle the problem and try to understand if you could work directly on the activations volumes, try to generate them back. But okay, just.
I think I found the paper. It's called the progressive growing of GANs for improved quality, stability, and variation.
Okay, can you link that?
Is it the paper from NVIDIA?
Yes.
Okay.
So, super complex model, not for continual learning. I think.
But continual learning is complex.
Yeah, of course.
Okay, so are there any other questions from the other participants?
I think I will create a channel called Meetup, so we can put a thing in it to not put in the general and other people would not understand why we put that.
Yeah. Yeah. So thank you very much for that. So, all right, we can maybe close this meetup. So thank you all for joining us today. And I hope to see you again for the next meetup online. And, just let's keep in touch and through the Slack Continual AI channel. So thank you very much again. See you.
See you.
Bye.
Thanks. Bye.
Bye.
Bye.